In this module, we are going to tie up the relationship between compactness and continuity. We are going to essentially study the interaction between these two concepts and derive several classical theorems that you might have learnt in calculus. Let me just state the first theorem, which is the most important of the lot. Let f from A to R be continuous. Suppose K subset of A is compact. Then f of K is compact. The proof is rather easy. Let yn in fk be a sequence. Okay. Let xn in k be such that f of xn is equal to yn. For each yn, there will be at least one such xn simply because yn is there in the image of k under f. By compactness, we can find a subsequence f of xnk that converges, we can find a subsequence xnk that converges to x in k. Okay. By sequential characterization of continuity, f of x and k must converge to f of x, which is there in f of k. So we started off with an arbitrary sequence xn in k. We started off with an arbitrary sequence yn in fk, and we have found a subsequence of that, which this we can just call ynk, which converges to a point in f of k, which means k is compact. The proof was fairly easy. Okay. Now we get an immediate consequence of this, which is the extreme value theorem. The extreme value theorem, which is as follows. Any continuous function on a compact set attains its maxima and minima. Okay. So to elaborate on this, that is, there exists m1, or rather small m comma capital M. Let's give this function a name, f from k to r. There exists small m comma capital M such that f of k is contained in the closed interval small m capital M, and there exists x1 x2 in k such that f of x1 is small m and f of x2 is capital M. This is an elaborate version of saying that a function on a compact set attains its maxima and minima. Why is this an immediate consequence of the previous theorem? Well, think about it for a moment. F of k is compact. Therefore, it is closed and bounded. And now we can just see that small m is infimum of f of k and capital M is supremum of f of k, and small m comma capital M will have to belong to f of k because this is closed. This is closed, right? And we are done. We are done. We have shown that the infimum and supremum belong to f of k. Therefore, there must be elements x1 and x2 in the set k such that f of x1 is small m and f of x2 equal to capital M. So, the extreme value theorem can be given a direct proof without resorting to any of this notion of compactness, etc. But notice that we have got a much more general statement. This statement applies not only to closed intervals, it also applies to any compact set. This is a course on real analysis, and you have just watched the module on the extreme value theorem.